Few days ago, I was partying with my friends. In the get together, we decided to discuss a very interesting topic. And the topic was how to stay young forever. Interesting, isn't it? While one group said that they would resort to a lot of physical activities like going to the gym, walking, swimming, jogging, the other group said that they would practice yoga and meditation. And there was this one more group which said that they would probably visit therapy clinics, beauty clinics, skin parlors, and eventually it had to happen. The question came to me, and I had two ideas in my mind to propose. The first one was that I would go and buy a supercar for myself and drive at very high speeds. Fast. Very, very fast. And the second thing that I would do is to move from the 20th floor of the building where I'm currently staying to the ground floor of the building. There was a pause for a moment, and then the entire group burst into laughter. They found my answer to be very strange and unbelievable. Some of the viewers who are seeing this video right now would be thinking the same, I believe. And in fact, one of my friends said, "How many pegs have you had till now?" Well, I had none because I don't drink, but what I said was absolutely correct. It is part of our daily life. Such phenomena are part of our daily life. We don't realize it because the quantum or the magnitude of it is very small. Strange, isn't it? But what's speed of the supercar got to do with aging? And what's height of the building got to do with aging? Well, welcome friends. Welcome to my channel, ASP's Brahmaand, where we will see our world, our universe where we live through the eyes of Albert Einstein and his theory of relativity. In the upcoming episodes, I will be covering the entire theory in two segments. The first segment is known as Special Theory of Relativity. The second segment is known as General Theory of Relativity. In Special Theory of Relativity, we will be covering 5 major topics. Starting with the first one, which is understanding the structure of space and time. In this, we have two theories. The first one was proposed by Newton, where he said space and time are absolute in nature. And the second one is the Einsteinian theory, where Einstein proposed that space and time are relative in nature, and time is a space-like dimension. And if time is a space-like dimensions, then we are living in a world of 4 dimensions and not 3 dimensions. And therefore, there is no such thing as space and time. In fact, there is only one entity, which is known as space-time. He further proposed that the dimensions can smoothly transit into each other, or the space-time dimensions can morph into each other, which brings us to our second topic of dimensional morphing. And he said that if dimensions can morph into each other, then there is a possibility of slicing the space-time structure where we are living in various ways. So you can imagine the space-time structure to be like a big cake, and you can slice it in various ways. Newton said that you can slice space and time in only one way. Einstein said you can slice it in various ways. The outcome of dimensional slicing, as we call it, are 2 effects. The first effect is known as time dilation, and the other effect is known as length contraction. This we will do in greater detail in the upcoming episodes. We'll try to understand in greater detail. Once we have understood the structure of space-time, dimensional morphing, slicing of dimensions, we then try to understand the cause and effect between events placed in the space-time structure or in the fabric of space-time. And this we refer to as geometry of causality. And we will take the help of the theory of light cones to understand the geometry of causality. After this, we'll come to our last topic in special theory of relativity, which we call it as the theory of fields. In theory of fields, we will try to understand the impact of field on the particle and the impact of particle on the field, the interaction between them. And yes, this theory of field is not quantum field theory. That's a different topic altogether, and we'll be covering in some other episode. This is classical field theory of what I'm talking about. Einstein was very happy when he came up with this theory of special relativity. But he was not too satisfied because he knew he missed something in this theory. Any guesses as to what he would have missed in special theory of relativity? Well, he did not consider the impact of forces in this theory. And we all experience a lot of forces, including gravity, in our daily life. So Einstein thought that his theory is actually incomplete, and special theory of relativity is a very idealistic theory, and he should consider impact of forces, and he did so. And he came up with his new theory, which was known as, or which is known as, the general theory of relativity, where he considered the impact of forces. In his general theory of relativity, Einstein found that under the impact of forces or the influence of forces like gravity, space-time bends, or what he called as warpage of space-time structure. So in special theory of relativity, he assumed that the space-time was flat and the bodies were moving on the flat space-time structure. But in the presence of a force like gravity, space-time bends. It bends like this. Now, this was a challenge because if space-time bends, then it is very difficult to predict the path of a body or the motion of the body in the bent space-time structure. And if we have to predict the path or the motion of the body, we need to understand this geometry of bend. You see this curve, this geometry we have to understand. Only then we will be able to predict the path and the motion of the body or the particle or planet. To derive or to define the geometry of bend, or what is known as curvature, required higher level of mathematics, very, very advanced level of mathematics. And Einstein was a physicist, he was not a mathematician. So he took help of his very good friend Grossman, who was a mathematician. And he tutored and facilitated and helped Einstein in understanding what is known as differential geometry. Einstein picked up differential geometry very fast, and he was able to finally define the curvature of warped space-time. And once he was able to define the curvature of warped space-time, he could also tell how a warped space-time creates tidal forces, which was proposed by Newton in his theory. But Einstein knew that even after finding the curvature say, defining the curvature, the theory was still not complete. It was still not complete. Because curvature was an effect. But what was causing curvature? What was the root cause? The cause was mass and energy. And so Einstein said that if we have the effect and mass and energy are the cause, then it is absolutely essential, imperative to link the two together. Only then we will have a complete theory in place. And he started working on the same principle. And finally, he came up with a set of equations which is known as Einstein's field equations, where he linked the mass and energy with which was the cause, with the effect, as we understand it, with the effect which is known as curvature. So once we understand how the space-time warps, how we define curvature, tidal forces, we understand field equations, we will then move a step ahead to understand the various type of stars, like white dwarfs, neutron stars, and black holes. Black holes we'll do in greater detail, of course, and we try to understand the structure, their properties, and once we have covered the stars, we'll move on to our next topic, which is known as gravitational waves. These waves exist, and Einstein had proposed at one point of time in one of his papers. So we have been able to detect the waves, these gravitational waves, with the help of very advanced lab observatories, and these observatories are known as LIGO, Laser Interferometer Gravitational Wave Observatory, and there's one more upcoming observatory known as LISA, and so we will understand these observatories and the technology behind it. And then post which will come some other topics or some very interesting topics in the theory of relativity. We'll try to understand the various scientific battles between various scientists, like, for example, Eddington versus Chandrasekhar, Robert Oppenheimer versus John Wheeler. So there have been many scientific battles, clash between theories, very interesting ones that we'll try to understand in the upcoming episodes. We'll also look at some very interesting papers by some of these scientists. My favorite being Sir Roger Penrose, who got the Nobel Prize for a paper that he had written a long time back. He got a Nobel Prize in 2020 on the singularity theorem of black holes. So many such papers will be discussed, and these are some very interesting topics. Friends, the universe is coded in mathematics, and therefore special and general relativity is very heavy in mathematics. But for everybody to understand, what I will do is to explain the theory with the help of a lot of diagrams, geometry, and some visualizations. People who are interested in hardcore mathematics, please put your comments in the description box. If you want it, I can have extended versions where we will discuss the mathematics behind these two theories. And I will come up based on your feedback. I'll come up with these episodes on your feedback. So friends, hop into my Starship and let's go cruising and explore our universe. I look forward to you in my next episode. Please join me. All the best.